Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Norifah Husna binti Muhammad Marzuki. So my matrix ID is MA18152. So for our experiment 2, which is free and forced heat convection. So the term heat transfer refers to the movement of the thermal energy as a result of a temperature difference. So convection is one of the three primary mechanisms of heat transfer, with conduction and radiation being the other. So the nature of the flow can be used to clarify convection heat transfer. So when a fan, a pump, or atmospheric winds are used to create a flow, it is called forced convection. So natural convection, on the other hand, is created by buoyant forces, which are caused by density differences caused by temperature changes in the fluid. So whenever it is not crucial to increase the value of the surface heat transfer coefficient or the temperature differential between the surface and the fluid, the addition of extended surfaces increases the heat transfer rate from a surface to a fluid. So fins comes in a variety of shape. However, only flat fins will be explored in this experiment. So this is the Newton's law of cooling, which specifies the rate of heat transfer from a surface to a fluid by convection. So here is the heat transfer plate with, and B is the without fins. So the objective for this laboratory is to learn more about heat transfer by convection, both naturally and artificially. The second one is to determine adding fins to a heat transfer system will impact the heat transfer properties. So for the experimental setup, we have fan, air duct, fin and flat plate heater inserts, power regulator, digital power meter, anemometer, plate heater placement, fan speed regulator, temperature sensor, and data logger with DESI lab software. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and good day to our beloved lecturer. My name is Nurul Izzati Shamim binti Uthman and my matrix ID is MA1809. Today I would like to present a lab heat convection. So my part is experimental procedure. In this experiment, we conducted two types of experiment, which is experiment 1 is a free convection. So here this is the procedure for free convection. The second experiment is forced convection, and also this is a procedure for the forced convection. And that's all from me. I will pass to the next presenter.
Hi everyone, I'm Akila Bintinut. My metric ID is ME18095. So for this experiment, we're focusing on collecting data of the heat transfer of free convection with cylindrical fin. So the power input that we've used is 75 watts and the ambient temperature is 31 degrees Celsius. At 5 and 10 minutes of time interval, we've collected the data for the final temperature, its efficiency, and the coefficient of convection heat transfer. Based on the data that we've obtained, I've plotted two graphs. The first one is the graph of temperature against time for free convection with cylindrical fins. So within 75 minutes of the time taken, it can be clearly seen that as when the time increases, the temperature of the cylindrical fins also increases. So the second graph that I've plotted is the graph of efficiency against time for free convection with cylindrical fins. So from the graph, it can be seen from 0 to approximately 45 minutes. The efficiency increases rapidly But after 45 minutes, the graph still increases, but it does not show a rapid increment. Instead, it shows a slow increment. So from this data, I can conclude that the purpose of convection fins is to lead heat from warm water in the radiator through the main body and out to a large surface area, which is in contact with ambient air.
So I will continue the calculation for the free convection. So Assalamualaikum, my name is Afifah Hamdia, MA18100. So the data was given by the manufacturer, so we got the data for the power, which is 75 watt, characteristic length or SC 110 millimeter, and we need to convert to meter. So we get 0.11 meter, and after that we got the diameter of cylindrical rod, which is 90.53 millimeter. So we need to convert to the meter. We got 0.00953 meter, and after that we got the data for the ambient temperature. So we got in Celsius, we need to convert to the Kelvin by adding 273. So we got the total ambient temperature in Kelvin is 304 Kelvin. So for the total surface area, we use formula pi df, which is the formula area for the cylinder. So since we use the cylindrical rod, so we get the surface area value is 3.2933 with exponential -3 meter. And after that, we need to calculate the average for the surface temperature by adding all the value of surface temperature, and we need to divide with the total number of data we take, and we need to convert it to the Kelvin. So the total is 332.1 to 67 Kelvin. And after that, we need to calculate the apparent temperature by adding the surface temperature with the ambient temperature, and we need to divide into 2, which is we get for 321.7 Kelvin, or in Celsius, which is 48.7. So for the beta, we need to use this formula, which is 1 over final temperature, and we got around 0.0031. After calculate all the data and convert into the correct value, we need to use interpolation. Since we got the value for the final temperature is 48.7, which is not in the properties of air in table A15. So after the interpolation, we got the value for thermal conductivity 0.027256.4, and for the kinematic viscosity 1.0964.2 with exponential -5, and for the final number 0.723138. After that, we need to calculate the relative number. Relative number, we need to use this formula, and we got the total. After substitute, we got the value is 4453.44. And after that, we need to calculate the Nusselt number by using this formula, and after substitute all, we get around 3.6290. And after that, we need to find the heat transfer coefficient. So based on the value that we calculate before, we get around 10.3792. And after that, we need to calculate the rate of heat transfer by using this formula, and we got around 0.9614 watt. And for the mass flow rate, we need to calculate by dividing rate of heat transfer with the coefficient and with the different temperature, and we got 0.03394 kilogram per second. And after that, the final formula that we need to use is total rate of heat transfer, which is N times VQ, or rate of heat transfer, and time rate of heat transfer. We got the final value is 23.0736 watt. I think that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zami Iqwan bin Mahrudin, MA18104. Okay, next I will continue. I will present the data collection for force convection. Okay, this is the table show the data from with film for force convection at fan speed B equal to 0.2 meter per second. So the data collect from we use with heat source power equal to 75 watt. Okay, next this is the result from the data. Okay, at the left it show the graph of temperature against time in minute of cylindrical fin for V equal to 0.2 meter per second for force convection. From the graph, it showed that when the time increase, the temperature also increase. Next, at the right, it shows the graph of efficiency against time of cylindrical fin for V equal to 0.2 meter per second. For the graph of efficiency for force convection, it also shows when the increasing in time, the efficiency also will increase. Okay, next, this is the data for fan speed V equal to 0.4 meter per second. Okay, this is the result from the data. Okay, at the right, it showed that the graph of temperature against time of cylindrical fin for V equal to 0.4 meter per second for force convection. Okay, it also shows when the time is increased, the temperature also will increase. And the right show the graph of efficiency against time of cylindrical fin for V equal to 0.4 meter per second for force convection. Okay, when time increase, the efficiency for V equal to 0.4 meter per second also will increase. Next, this is the table for fan speed for V equal to 0.6 meter per second. In force convection, all we use heat source, same power, that is 75 watt. Okay, this is the result for the data from the data. Okay, at the right, at the left, it shows that when the graph of temperature against time of cylindrical fin for V equal to 0.6 meter per second, it shows that when the temperature will increase, the time increase, the temperature also will increase. And at the right, show the graph of efficiency against time of cylindrical fin for V equal to 0.6 meter per second for force convection. It also show when the time is increased, the efficiency for V equal to 0.6 meter per second also will increase. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Khairul Adhani binti Khairul Nizam. My matrix ID is MA18102. I will continue the presentation from previous presenter. I will talk about the calculation for forced convection. I will talk about the sample calculation for forced convection. So, the example I use is the power input with 75 watt and velocity 0.2 milliliter per second, meter per second, sorry. Then we will, the ambient temperature is obtained from, ambient temperature is fixed. So therefore, the ambient temperature is 31 degrees Celsius. Then we will calculate the average for surface temperature and the average for film temperature. The average of the surface temperature is 86.65 degrees Celsius and the average film temperature is 58.90 degrees Celsius. Next, we will move to the calculation. Okay, for the to obtain the thermal conductivity, kinematic viscosity, and Prandtl number, we have to refer to appendix which is the table A15. So once we obtain all the values, we will calculate the velocity maximum. Okay, to calculate the velocity maximum, as you can see, we have ST and SG. Okay, both values can be obtained from the distance of center from one cylindrical rod to another cylindrical rod. ST is the straight line, while the SD is the diagonal distance of the center from one cylindrical rod to another cylindrical rod. Then the diameter of the cylindrical rod is 0.009593 meter. So we put all the values inside the formula. Then we will obtain the velocity max is 0.3947 meter per second. After that, we will calculate for the Reynolds number. The Reynolds number calculate was 199.62. Okay, from the Reynolds number, we will calculate the Nusselt number. The Nusselt number can be obtained from table 7.2. Okay, as you can see, the Reynolds number is 199.62. It is below than 500. So we will use this formula to calculate for Nusselt number. So we get the Nusselt number 7.7067. After that, we will refer to table 7.3 to get the F value. After we get F value, we will calculate for the heat transfer coefficient. We get the heat transfer coefficient is 21.73 watt per meter square dot Kelvin. Then we will calculate the total surface area and the rate of heat transfer. After we will calculate both of these values, we will calculate for the mass flow rate and total rate of heat transfer. As for the total rate of heat transfer, the number 24 is from the type of fin we would use. Due to we use the cylindrical rod, so the value of the N is 24. So the value for mass flow rate and the mass flow rate is 0.0712 kg per second and the total rate of heat transfer is 95.7744 watt. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Razia, metric number MA18092. I will be explaining the discussion part of this report. I will be mainly answering questions from the lab sheet. So the first question is discuss free convection and forced convection. Free convection, also known as natural convection, is a type of convection heat transfer in which the fluid molecules move to transfer heat due to a density and temperature gradient. As a result, a buoyant force is exerted on the molecules in the lower layer, causing these molecules to migrate upward. As for forced convection, it is a type of convective heat transfer in which the mobility of molecule is caused by the application of heat from an external source. Forced convection has a faster rate of heat transmission that can be adjusted by external devices. As a result, the forced convection system has a higher overall heat transfer coefficient than the free convection system. Next question, discuss laminar flow, turbulent flow, and heat coefficient. Laminar flow occurs when a fluid flows in a parallel layer with no interruption between them. The motion of the fluid particle is exceedingly ordered in laminar flow, with all particles traveling in straight lines parallel to the pipe walls. As for turbulent flow, it is characterized by erratic property changes in the flow. This involves changes in pressure and flow velocity that occur quickly in both space and time. Unlike laminar flow, the fluid does not travel in layers and mixing across the tube is extremely efficient. Flows with Reynolds number greater than 4000 are usually turbulent, while those with a Reynolds number less than 2300 are usually laminar. Transitional flow is defined as flow with Reynolds number ranging from 2300 to 4000. As for heat transfer coefficient, when the fluid velocity rises, the heat transfer coefficient rises with it. The heat transfer coefficient works as a proportionality constant in Newton's law of cooling. The heat transfer coefficient will still fall throughout the length of the surface, although not as much as in laminar flow. A turbulent flow, on the other hand, can be advantageous or disadvantageous. A turbulent flow increases the amount of air resistance and noise, but it also speeds up heat conduction and thermal mixing. Understanding, managing, and controlling turbulent fluxes is so important for successful product design. Next question. Discuss the difference in the measured value of heat transfer coefficient if one uses linear average temperature instead of LMT. So LMT or LMTD is logarithmic mean temperature difference. It is an average of the temperature difference between the hot and cold feeds at each end of the double pipe exchanger. For a given heat exchanger with constant area and heat transfer coefficient, the larger the LMTD, the more heat is transferred. LMTD can be calculated using this formula where TA out is the secondary fluid out temperature, TA in is the secondary fluid in temperature, and TS is the steam temperature. As for the linear average temperature difference, or also known as AMTD, it is in linear average temperature method. We need to find temperature difference on the whole length of the heat exchanger. Then find the mean by dividing the sum of the temperature. In the AMTD, to find accurate temperature difference, we would have to measure temperature difference at all the points, but practically it's not possible. So if we use AMTD, then there would be error present in the calculation. Therefore, it is recommended to use LMTD. Next question is discuss the effect convection mode on the efficiency. Convection involves real movement of fluid particle for heat transmission, whereas conduction involves just privation of the particle at their place for heat transfer. As a result, kinetic energy transfer in convection is faster than in conduction, making convection the more efficient method of heat transfer. Next question is on the effect on extended surface on the heat convection. The amount of heat transported is proportional to the area. The area accessible for heat transfer rises when expanded surfaces are used. As a result, the amount of heat transported rises. The term fin is used to describe these stretched surfaces. To maximize the rate of convective heat transmission, fins are frequently built of highly conductive material like aluminium. An automobile radiator is an excellent example. The rate of heat transfer to the surrounding ambient is substantially aided by these thin plate fins. And lastly, discuss our findings. Based on this experiment, we found out that forced convection surpasses free convection due to its higher heat transfer coefficient. It's because the rate of heat transfer and other variables had the highest value when compared to free convection. The bigger surface area for heat convection also produced a larger value. Therefore, the surface area is increased by combining the stretched surfaces. By increasing the surface area and adding extended surface to the surface, the rate of heat transmission to the surrounding ambient through the thermal convection process is greatly improved. That's all from me. Thank you.
So, in conclusions, the forced convection performs more better than the free convections. This is due to the heat transfer coefficient, the rate of heat transfer, and a few other variables in the forced convection shows higher value compared to the free convection. While in terms of the factor of extended surfaces, which is as known as fins, to the surface tend to the increasing rates of heat transfer to the surrounding ambient through the heat convection process. I think that's all from me. Thank you.